Hey everyone, so today we're going to be talking about the spectroscopy of aldehydes and ketones. And so some of the spectroscopies we're going to be talking about is IR, infrared spectroscopy, looking at the vibrational absorption spectrum of these aldehydes and ketones, mass spec and the potential ion fragments you get from that, and then NMR, both C13 and proton NMR. All right, so with IR spectroscopy, aldehydes and ketones, which you guys are familiar with, have very active IR absorption peaks, and it's most distinguishable. Both of these are any compound with a carbonyl carbon. They have a strong carbonyl stretch present in the compound, and that's usually around 1700 inverse centimeters. Aldehydes also have a characteristic CH stretch, right? Because we have a extra hydrogen that's bonded to the carbonyl carbon, right? So there's an extra hydrogen there that then exhibits its own um, vibrational mode that absorbs in the IR region. And so things like aromaticity, conjugation, and ring strain can also have an effect on the position of the characteristic carbonyl stretch. And so you can imagine, depending on the types of group or this force geometry of the molecule, that affects how tight the so-called springs are that hold the atoms together are constrained, and then that affects their vibrational frequency. For example, if you compress a spring a lot, and then you were to try and vibrate it, it would vibrate at a higher frequency than if it was an extended spring, for example. And one thing that's kind of interesting about our spectroscopy for aldehydes and ketones, you can actually use this as a pretty um, thorough method for distinguishing between different aldehydes, ketones, um, within that, their own realm, um, because they have distinct peaks and the positions are very consistent between molecules. So, for example, if you have a CO stretch at 1730, as opposed to a higher number, then it's almost always going to be an aldehyde over a ketone. And then if you have a carbonyl stretch in the 1750 region, that's almost always specific to cyclopentanone, right? So cyclopentanone is going to look something like this. And that's because the force geometry of this angle right here affects the vibrational frequency of that bond, right? So that angle, because a pentagon is going to have a different angle than what the natural trigonal planar sp2 carbon would have, which would be a 120-degree angle, is going to have a tighter angle, and then that's going to affect the actual vibrational frequency of the carbonyl compound. And so if we look at these specific values, that can actually tell us a lot about the structure itself. And so these are unique to the carbonyl motif. And so some examples, a saturated aldehyde is going to have an absorption peak around 1730, aromatic aldehyde 1705, and then all of the different cycle ketones are going to have larger frequency absorption peaks. And so as we strain the ring more, um, we're going to basically put more tension into the carbon oxygen bond, and then that's going to cause it to vibrate at a higher frequency. And so based off of, these specific values, these are pretty well correlated with their associated structural motif. And so carbonyl IR spectroscopy can actually be used pretty well to distinguish between the different aldehydes or ketones that you have. Two examples here, we see the difference between benzaldehyde and a cyclohexanone. And we look and we see that the peaks right here of the carbonyl are relatively shifted to each other, like what we would expect from the previous slide here. So these peaks are relatively shifted to each other, and there's a couple other features that are important here. So aldehydes, they tend to have this double peak in the 2700 to 2800 centimeter range. And this is the carbon hydrogen stretch in the aldehyde itself. And so this is always characteristic of aldehydes. This 2700 to 2800 double peak is characteristics of aldehydes. And then looking at the rest of the molecule, those are the two kind of distinguishing features for aldehydes versus ketone here is the the carbonyl stretch that we have in both of these compounds and the double peak that we see in the 2700 to 2800 region for aldehydes. If we look at um, the ketone, we can the ketone we can see some other distinctive features there. Over here we have a lot of the carbon-carbon stretches within the ring itself. Here we have the carbon-hydrogen stretches, the CH2 stretches on the outer part of the ring. And then if we look at aldehyde up here, this would be where the carbon hydrogen stretches and wiggles are for the aromatic compound, right? So the aromatic stretches are a little bit different here. And so this is kind of like the main way that we would distinguish between an aldehyde and a ketone. If we were to zoom in even more at this peak, we would be able to distinguish even farther based off of the relative shift here, right? So the resolution here isn't that high, but you could look at the position of that specific peak, and then that would give you even a better idea of distinguishing these two compounds, especially using IR spectroscopy. So for the next spectroscopy we're going to be talking about, we're going to be talking about mass spec, right, where we ionize a molecule, send it through a gas chamber, it hits a sensor, and then based off of the distance that is traveled, we get a mass to charge ratio um, for the compound, and then that gives us an idea of the different fragments that are breaking off from the compound. And so for mass spec, there's two main mechanisms for ionization of aldehydes that I want you guys to know. So the first two things you're going to always have is you're going to have the molecular ion. So if we have an aldehyde or a ketone, a generic one, the molecular ion is just going to be the ionized version of this entire molecule. So we don't know exactly where it's going to ionize, but we know that it's going to have a positive charge on it somewhere. Or for the ketone, it would be the exact same thing. So that's going to be the first, or one of the first peaks that you're going to see in the iron, not actually along the axis, but that'll be one that's always going to show up. The other two that you're most likely going to see are due to specific rearrangements that occur from ionization of the molecule. And the first one is called a McLafferty rearrangement, which you guys have probably seen in a previous Oken course. And this is a rearrangement on the gamma carbon in a ketone. So if we're looking at a aldehyde or a ketone, so this could be an aldehyde, for example, this is the alpha carbon, this is the beta carbon, and then this is the gamma carbon, right? So this would be the rearrangement on the gamma carbon. And so this is kind of a pseudo ring rearrangement because of the way it kind of breaks and cleaves bonds to make the two ionic fragments. The other one is going to be an alpha cleavage, and that's going to be rearrangement from the alpha carbon here, right? So this is going to be, if we have an arbitrary ketone here, R, R prime, the alpha carbon is where we're going to see this rearrangement and fragmentation in the mass spec. And the reason these are important is because these can help you distinguish the two ion fragments that you're going to see in mass spec. And so let's look at how the rearrangement and cleavage actually happen in the mass spec. The McLafferty rearrangement. Again, it's the rearrangement dealing with a cleavage at the gamma carbon's position. So if we had an arbitrary structure that looks something like this, we have a hydrogen atom. This is going to be our gamma carbon right here. It's our beta carbon, our alpha carbon, and then our carbonyl carbon. So I've drawn it this way just because it's easier to show the rearrangement in this case. So this is our beta carbon and this is our alpha carbon. Our carbonyl carbon, these can be hydrogens or other groups that are over here. And we get a rearrangement of this hydrogen on the gamma carbon that then forms an alcohol with the ketone. So we're going to have the carbonyl, the bond rearranging here from the carbonyl carbon. and then we get cleavage between the beta and the alpha carbon here. And so the two molecular fragments that we then get, so this is after ionic rearrangement, is we're going to get the gamma carbon double bonded to the beta carbon with the R group here, and then the carbonyl carbon double bonded to the alpha carbon with an OH group. Now, um, where the carbonyl oxygen was. So this is the gamma carbon, this was the beta carbon, and this was the alpha carbon, right? So these are two molecular ions, and the charge is going to stay with this alcohol or this enol ion, right? So the charge is going to stay over here. So this is the molecular ion that you're going to see in the mass spec. The alpha cleavage, as the name suggests, we're going to have cleavage at the alpha carbon in the ketone or aldehyde. So we have our ionic fragment. We get the alpha cleavage, and we get radical with the first R group on it, and then we get a mix of two uh, ion ions that rearrange with respect to each other. So we get a cleave between the, right? So this would be where the alpha carbon is here. We get cleavage between this bond, and that's why we have the R group on its own. And then this has a resonance with having the positive charge on the carbon and the positive charge on the oxygen. And this molecular fragment is going to be the acyl group, right? So this is the acyl group, acyl molecular ion, and that's what shows up in the mass spec. So the two things that show up in the mass spec based off the type of um, rearrangement that you have are the ones that are highlighted in green here. So these ones are the ones that show up the mass spec. And so you would really only know the M to Z ratio after looking at your mass spec and would be able to tell beforehand. But if you saw this peak separation, you saw one with the full molecular weight to charge ratio, and then you saw two other ones, one with a slightly higher charge ratio, which is going to be from the McLafferty rearrangement, and then one with a lower charge ratio, which would be from the alpha cleavage. You would know, you'd be able to then figure out what the two molecular ions were that were created in this case. And so we can go through an example of that, of what that would look like. So for example, if you were given a mass spec and you know that you had this compound, which will be 5-methyl 2 pentanone, 5-methyl CH2 CH3, 5-methyl 2 pentanone. Or if we were to draw the carbon skeleton for that, it would look something like this. You would have two peaks, one from the alpha cleavage. I'm just going to use the Greek letter because it's easier. And then another one from the McLafferty rearrangement. The McLafferty rearrangement, you know you need a gamma carbon. So in our original structure, this would be alpha, beta, gamma, right? So you need a gamma hydrogen for this to be able to happen. And so then you would know the cleavage would happen between the alpha and the beta. So the molecular ion fragment that you would see would be OH here. This would be our active molecular ion that would show up in the mass spec. Then from the alpha cleavage, we know that we would get the acyl group, which would have C double bonded O positive CH3, and then this would have a resonance with the positive charge on the oxygen as well, CH3, right? So you could potentially get these two molecular ion fragments. So if you were given a mass spec, you would be able to then determine, if I told you it was of this molecule, what are the molecular ion fragments, associate them with a peak. You would be able to do that. Okay, so that would be it for mass spec. The next thing we're going to talk about is NMR spectroscopy, which is probably our most powerful tool in structure identification and compound identification. And so with H1 or proton NMR, ketones don't really have a distinctive absorption peak compared to aldehydes, because if we have an alpha carbon there, those tend to be a little bit deshielded, but there's no associated proton that distinguishes a ketone from an aldehyde. And so hydrogens on the carbonyl near an aldehyde, however, do have a distinct absorption in the NMR spectroscopy, proton NMR spectroscopy. And that's because this proton right here, right, is very deshielded because it's right next to the carbonyl carbon. And this gives an absorption in the 2 to 2.3 parts per million range, or a 2 to 2.3 delta value, whereas usual kind of CH2 groups and whatnot are going to be between 1 and 2 ppm, right? So if you see a peak, and this is just going to be either a single peak there, and to say that this is actually the alpha carbon protons that are here, which are, that's why I compared it to the CH2 values. Those are going to be absorbing in the 2 to 2.3 ppm range, right? And so these are going to have a doublet because these protons right here are going to be coupling to the aldehyde proton, right? And so we get n+1 peaks, so it should be a doublet for each of these. And then if you were to integrate this, you would get a value of 2 to let you know that it was these two hydrogens that gave the same signal here. And so this would be assuming also that this chain is continuing as well. And so that is a signature of an aldehyde, this doublet at the 2.2 to 2 to 2.3 range, because these protons are going to be pretty deshielded from the carbonyl carbon here, and they're going to be coupling to that hydrogen. So that's why we get a doublet. We also have an aldehyde proton, right, which is in blue, and these usually couple to the alpha carbon protons, right? So that would be these protons right here. These ones couple to the aldehyde proton, and then the aldehyde proton is also going to couple to these alpha protons. And so that can either be a triplet or a quartet, depending if it's something like ethanol or something like that. That'll give you a quartet. If it's any other aldehyde, it'll give you or any other aliphatic aldehyde, it'll give you a triplet, because we have two protons per couple two. And so this is going to absorb in the ppm range of about 10, and this is unique to aldehydes, right? So no other protons absorb in this range. And since no other protons absorb in this range, if you see a ppm peak around 10, and if you were to integrate this, that signal will give you an integration of 1. That is your aldehyde proton. So that's going to be indicative of an aldehyde. And so that's true for proton NMR, but we also have carbon-13 NMR. And in that one, we're looking at the specific carbonyl carbons. And so the carbonyl carbon has a distinct absorption. No carbon has a distinct absorption in the 200 ppm range, where no other carbon nuclei are going to absorb there. And so in this 200 ppm range, if you see anything there, that tells you that 100% that you have a carbonyl carbon. The specific value, so if it's a lower value of around 190 to 200, that's usually going to be associated. Sorry, not 190 to 200, but 190 to 200 is usually going to be associated with a aldehyde. And then the larger values, 200 and larger, are usually going to be associated with ketones. If you have an aromatic ring there, that's also going to affect slightly the absorption of this carbon as well. But 190 to 200 is for aldehydes, and then 200 and larger is usually going to be for ketones for these for the NMR of aldehydes and ketones for carbon 13 NMR. Two examples of this, we have benzaldehyde and ethanol. We see that this is just going to be your solvent peak here for both of them. Solvent peaks. Here for the um, aldehyde, we see that we have a strong absorption in the ppm equals or delta value of 2 here. This is going to be for the protons. Let me do this in a different color. The methyl group protons attached to the carbonyl carbon. And so if you were to integrate this singlet, you would get a value of 3 because there's 3 protons that are coupling to the aldehyde proton, and those are slightly shifted downfield because they are going to be de-shielded. So that's why it's in the 2 to 2.3 range, right? So that's why we get a value there. And then we also have a value in between 9 and 10. And if you were to integrate this, you would get a value of 1 because this is actually going to be the aldehyde proton that's coupling to each of the methyl protons, right? So if you were to zoom in on that signal, you would probably see that it has a quartet because it's coupling to three protons there. And then if we look at the benzaldehyde example, we see that we don't see a value around the 2 here, like we did in ethanol. So you don't see a peak here at all. And so why don't we see that? Well, if we look at this structure, we see that the closest protons would be over here. So the distance is a little far. So this H can't couple to the aromatic protons. And so these can't couple to the aromatic protons. And so that's why we don't see a peak around 2 because there is no proton. That's going to be right here. We look at the peak here at the right. Actually, sorry, it's not that these can't couple to the aromatic protons, but rather that these ones can't couple to the aldehyde proton. Can't couple to the aldehyde proton. And then this peak right here is going to be the aldehyde proton, the aldehyde proton. So we have the aldehyde proton, and then these peaks over here, these are all going to be the aromatic protons. And those ones we talked about in the chapter on aromaticity, those are shifted downfield a bit because of the ring current that we get in the aromatic pi system here in the center of the benzene ring. And so that's how we would look at 2 examples of NMR spectroscopy. This is all going to be proton NMR, which we are going to be using mostly in our class, to then distinguish between aldehydes and ketones, and to see if we have carbonyl carbons or if we have hydrogens near carbonyl groups in our structures. And so that'll be it for the spectroscopy of aldehydes and ketones. And next we're going to be talking about carboxylic acids and nitriles.